Hi, and welcome to Meetings in Math. You are here for 7.5C, Scaled Drawings Practice, Part 2. Your essential question for today is, how can I use a scaled drawing? Today you will need your Jaguar Jots on 7.5C, a pen or a pencil. You might find a highlighter helpful, your best effort, determination, and as always, bring your problem-solving skills. Let's take our scaled drawings now into the three-dimensional realm. Here are some drawings of a school bus, a quarter, and the subway lines around Boston, Massachusetts. The first three drawings are scaled drawings of these objects, and the next three drawings are not scaled drawings of these objects. What do you think a scaled drawing is? I want you to take a moment to examine these, write down what you think, and then I will talk about them a little bit more. So one of the things that you'll notice is that a scaled drawing is a copy. It shows the object accurately and all the parts in the drawing match all the parts in the actual object. No parts in a scale are distorted. So the school bus is a really good example. The first one, it looks almost like I took a picture of it. And the second one looks definitely like I hand drew it. It would look a lot like if I tried to draw one. It kind of scoops in where it's not supposed to scoop in. And the wheels look a little kind of flat almost, and like they might not quite make it down the road, where the first one looks more like I took a picture of it. It's like a scaled copy of a real object, but the drawing shows the flat surface of the object. Just one flat surface. So now that we talked about what a scaled drawing is, let's look at these scaled drawings of different buildings. We have the Great Pyramid, the Eiffel Tower, Willis Tower, CN Tower, and Burj Khalifa. And we're looking at a scale of 100 meters is this long. It depends on what we're looking at. Is it an inch? We don't know. Depends on however it was copied for you. So for me, it is this bar right here. There are two different ways you can do this. You can either take your piece of paper and on the edge mark that out and then bring it over to Willis Tower and put the tick mark straight onto Willis Tower. Or you can take your piece of paper and mark out Willis Tower's length and then take it back over to this and then mark off tick marks on that line that you have. I personally like to take and mark this out and then come over to Willis Tower and I will mark up Willis Tower. So that's what I'm going to do. So I took my bar, and now I know how big my bar is, and I copied it, and I'm going to mark up Willis Tower with however many bars I have. So I have 1, 2, 3, 4, 5 bars gets me to the top of Willis Tower. I know each one of these bars is 100. So I have 100, 200, 300, 400, 500. Because it's 5 bars tall, 5 times 100 is 500. So Willis Tower is about 500 meters tall. So what about the Great Pyramid? Same idea. This is 100 meters. So now I have to figure out how many goes on here. So there's one, and there's another one, but that's too tall. So 1 was too little, but 2 is too tall. So now I need to figure out, well, where does that hit? About, where is it? So it's about there. So it looks like it's about halfway. So it's about 1 bar and half of another. So I know each bar is 100. So I can say 1.5 times 100 is 150. So it's about 150 meters tall. So about how much taller is the Burj Khalifa from the Eiffel Tower? So I could go figure out their total height and then subtract them. I absolutely can do that. But that would require 2 conversions when really I only need to do 1. So I know that's 100 meters right there. So the Eiffel Tower is 1, 2, 3 bars tall. And the Burj Khalifa is 1, 2, 3, 4, 5, 6, 7, 8 plus a little bit more. So 8.5, we'll call that 8.5 bars tall. So looking at just the bars, I can say Eiffel Tower is 3 bars tall and the Burj Khalifa is 8.5 bars tall. So we know that there's a 5.5 bar difference. So really all I care about is that difference, right? Because it said how much taller is it? So just multiply the difference by 100. I don't really care about the first 3 bars because that's the Eiffel Tower. So these first 3 bars I don't care about. All I care about is the difference. Well, and the top part doesn't matter either. So the difference is 550 meters. Now, could have I gone and done the double conversion? Yes, you absolutely could have. You could have said that this was 300 meters, and you could have said that this was 850, and then you could have said 850 minus 300 equals 550. But you would have had to shown the conversion for the 300 and the conversion for the 850. Here, you only had the part in the rectangle, you only had to show one conversion. Measure the line segment to the nearest 1/10 of a centimeter. The scale of the drawing is, okay, this one really depends on how yours is done. We do know one thing for fact is that we are talking about 100 meters. What we don't know is how many centimeters yours measures out to. It all depends on how yours is printed, but it should be about 0.7 centimeters. If you are looking on a computer screen like I am, it's much bigger. It's probably closer to 1.5 centimeters. If you are looking at the print, it should be about 0.7 centimeters. The Westland Lysander was an aircraft used by the Royal Air Force in the 1930s. Here are some scale drawings that show the top, side, and front views of the Lysander. Let's find the wingspan of the plane to the nearest foot. So when we're looking at the wingspan, what we are looking at is how far is it from this tip all the way to this tip. And we have 2 scales. We have a foot scale and a meters. And this one's saying to the nearest foot. So we are going to use this smallest one. So again, take out a piece of paper and either measure from edge to edge or take a measure from here to here. I found that it was easier to measure from edge to edge and then take it down to here and then mark off how many of these that you have. But for purposes here, that's how long it is. And then I have 1, 2, 3, 4, 5 and a little bit more. And when I figured that out, it was 6/10. And basically each one of these was 1/10 of this. So there was 4.6 segments and each segment is 10 feet long. So what are we going to do with those 2 numbers? We are going to multiply those 2 numbers together and we end up with 46, which means that the wing segment is 46 feet long. So now let's look at the height of the plane to the nearest foot. So the height means from the wheel all the way up here to the tip. And I found that it was easiest to measure on this one, although it might have been easier to measure on this one. But this is the one I measured off of. So again, for my length of my scale, because we're still using feet, I did 1 and then my second one, but you can see it didn't quite go all the way. And I figured that was about 0.2. So what am I going to do with those 2? I'm going to multiply them together and I get 12. So it was 12 feet tall. So let's find the length of the plane to the nearest meter. So for the meter, we're using the longer one because it's meters. And I used this diagram right here. And so the tip to the tail. So I found the meters and I laid it out once and twice. And so again, we see it's not quite long enough. So I figured that was about 0.3 of the longer one. So there's about 1.3 and each segment is 7 meters long. So we are going to take 1.3 and times it by 7 and we get 9.1. So it's about 9.1 meters long. So in this last one, a blueprint for a building includes a rectangular room that measures 3 inches long and 5.5 inches wide. So that's the small one. The scale for the blueprint says 1 inch is 10 feet. What are the actual length and width of the room in the building? So for the length, we are going to take the 3 inches and do what with it to find how many feet it is? Well, we know it's feet per inch. And let's go ahead and do this by proportions. We know it's 10 feet for every 1 inch is the same as, we don't know how many feet we have, but we do know it's 3 inches. So to undo division, we multiply both sides by 3. And this is why all we've been doing is multiplying 10 times 3, because you can see that's all we're going to do here. And we get 30. So if I had just gone 3 times 10, I would have had the same answer. But this is why it's been working is through proportions. So it was 30 feet. So let's look at the width. Again, we have feet per inch. So we know that for every 10 feet, we have 1 inch. So we don't know how many feet, but we do know we have 5.5 inches. So we are going to multiply both sides by 5.5. So 5.5 times 10 ends up being 55. So 55 is equal to F. So we have 55 feet. Again, if you had just multiplied 5.5 times 10, you would have ended up with the same thing. But it's because of proportions that this has been working. I want to thank you so much for joining us in Scaled Drawings Practice. And what I would like you to do to finish up this lesson is find at least 2 examples of scaled drawings around you. Think about the different things that we've used for scaled drawings and find at least 2 examples around you. If you can't find 2 examples around you, think of 2 examples that you'd be able to find in real life. Thank you again so much for joining us. And remember, be kind to one another because we can all use some extra kindness in our lives. And I'll see you in our next lesson. Bye for now.